Assalamu alaikum everyone and a very welcome to my presentation. My name is Jubayer and today I will be presenting a research paper review for my course Cryptography and Network Security. Um, the the paper is titled as Enhancing Optimatic Diagnosis with Assembly Deep Learning Combining CNNs and Transformer for Multi-Class Eye Disease Classification. This paper was published 2005 IEEE AIBThings International Conference, the third international conference on artificial intelligence, blockchains, and Internet of Things. And it was authored by researchers including MD Fakhrul Islam Khan, Abdul Kader Muhammad Masoom, MD Maruf Hassan Sir, and also others. Uh, over the next 30 minutes or so, I will discuss about this paper with you guys. So let me first give you a quick roadmap of the paper what we'll be covering today. So first, we start with the background of the study, where I will explain why eye disease are such a serious global health problems and why deep learning is being used to address it. And then we will talk about the research gap, where we look at what existing studies have done and what important piece they were all missing. And then we will talk about the problem statement, which describe exactly what the challenge this paper is trying to solve. And then we will go with scope of the research, which defines the boundaries of what this study covers. And then literature review, where we look at others like 6 prior research works and compare them with ours. And then we will talk about the methodology, the technique heart of the paper, how the models were built, trained, and combined. And then we will talk about resultant analysis, where we look at the accuracy number and the charts and what they mean. And then we will talk about the future work, what the author says should be done next. And then the reference, where all the reference will be given. Now talk about the now let's start with the background to understand why this paper matter. We first need to appreciate the scale of the problem it is addressing. According to the World Health Organization 2019 World Report on Vision, more than 2 billion people across the globe suffer from some form of vision impairment. This is roughly one in every 4 people on the planet. Many of these cases are preventable or treatable, but only if diagnosed early enough. Now, let's look at the specific eye condition this paper focused on, like cataract, conjunctivitis, and then eyelid disorders, and then uveitis. So let's talk about them. Like cataract, this is the leading cause of blindness in older adults. It affects the lens of the eye, causing it to become cloudy over time. Vision become blurred, like looking through a foggy window, and without treatment, it can lead to complete blindness. And then conjunctivitis. This is commonly known as pink eye. It causes redness, discharge, and irritation in the eye. It spreads very easily from person to person, making it one of the most common eye conditions seen in clinics. And then we have eyelid disorders. These are problems that affects the eyelid itself, such as dropping, inflammation, or misalignment. If not treated, they impair the normal hygiene and protective function of the eye. And then the last we have uveitis. This is a inflammation of the middle layer of the eye called the uvea. It is peculiarly dangerous because if left untreated, it can be damage. It can damage the optic nerve and cause permanent vision loss. So now let's talk about on this right side. I want to explain why researchers are turning to deep learning to solve this problem. Like all of this is kind of medical problem. So why are we going to deep learning for this to solve this problem? So let's talk about that. First, deep learning models learn features automatically from raw image data. This means doctors do not need to manually define what to look for in an eye image. The model figures it on on its own without from thousands of data that are available by training them. And then second, CNN, a convolution neural network, have already proven highly effective in detecting other eye diseases like diabetic retinopathy or glaucoma. Those are I found in web. So there is strong evidence that this is approach works in ophthalmology. This all information I am giving is from web. So and then third, we have like transfer learning, where you use models pre-trained on a large data set like ImageNet, and fine tuning it for your specific task. Significantly reduce the need of large medical data set. This is critical because medical image data is expensive and difficult to collect. That's what I experience also. And then transformer models like specifically the vision transformer and Swin transformer use a mechanism called self-attention to capture long-range spatial relationship across an entire image, something traditional CNN struggle with. And then we have early detection. Early detection of these diseases can genuinely prevent irreversible vision loss. So the stakes are extremely high, which is exactly why we need AI systems that are fast, accurate, and reliable. And then we will talk about the research gaps. What have what already exists, like research have accessibly studied CNN-based models like ResNet and like Inception V3 for detecting retinal disease. These are strong models, and they have shown good performance in control settings. And also something like transformer models, Beat or Swing, Swin transformer or vision transformer have also been explored for image classification tasks and have achieved impressive accuracy numbers. And then transfer learning using pre-trained models on ImageNet has been shown to work well, even medical dataset are small. And then several individual models have achieved between 92 to 98% accuracy on a specific eye disease task. And then and some studies have also used smooth systematic monitoring overlapping techniques to deal with uneven class size in the training data. So all these are what already exist. So now we will see what the gap was in those papers. Like CNN and transformation have been studied separately. Very few studies have ever tried to combine them. This is a huge missed opportunity because these two types of models have completely strength. CNNs are excellent at detecting local textures and fine patterns, while transformers are excellent at understanding global context and long-range relationship. No prior studies has combined all four of these specific models like ResNet 50, Inception V3, Vision Transformer, and Swin Transformer into a single unified assemble for classifying external eye diseases. Class imbalance was also often ignored. Like for this, many accuracy were high, but in the end it was not because of class imbalance. In many existing datasets, some diseases categories have far fewer images than others, which cause models to become biased. Like sometimes accuracy high, sometimes low. No assemble had been tested on all 5 conditions together, like uh, like cataract conjugation eyelid, these at the same time মানে একসাথে no assembled tested on not ever happened, and there were limited focus on visual similar classes. For example, conjunctivitis and eyelid disorders can look very similar in photographs, and most individual models struggle to tell them apart. This gap, the absence of combined CNN and transformer assembly of all 5 external eye diseases, is exactly what this paper does. Now let's state the problem clearly. Eye diseases affect over 2 billion people worldwide, yet diagnosis remains slow and inaccessible in many regions. Existing deep learning solutions use either CNN or transformer, but not both together. CNNs excel at detecting local texture feature, while transformer capture global separate context, and no prior study have combined all four of these leading architectures into a unified assembly for classification all five major excellent eye conditions. This is the core problem the paper is solving. Now let's break the problem down into four specific technique challenges, like class imbalance, and then single model limits, and then visual similarities and clinical reliability. Let's talk about class imbalance. When the training data set has unequal number of samples for each disease categories, the model ends up biased towards whichever class has more image. It learns to recognize the common classes well, but perform poorly on the rare ones. This is a fundamental problem in medical machine learning. And then like visual similarity, conjunctivitis and eyelid disorders look remarkably similar in photographs. Both cause redness and swelling around the eyes. A model that cannot distinguish between them reliably in dangerous in a clinical settings, because the treatment for these two conditions are different. Single model limitations. Any single models, no matter how powerful, can only extract features in the way it was architecturally designed to. A CNN captures local patterns but miss the big picture. A transformer captures the big picture but many miss subtle local texture. Using just one model means you are only getting half the information. That's why this paper uses both. And then clinical reliability. In medical diagnosis, even a small error rate has consequences. If a model misclassifies, let's say, URIVAs as conjunctivitis, the patient does not get the right treatment and could suffer permanent vision damage. So medical also he can die. So medical AI system must achieve extremely high accuracy, not just good accuracy. And then we will talk about the scope, exactly what this study covers and what it does. Like let's say target classes. The study focus on 5 specific external eye conditions. I already said cataract, conjunctivitis, eyelid disorder, uveitis, and then normal. These are all conditions that are visible in a photograph and of a eye external surface. No internal image equipment like a MRI or retinal scan is required. And then the data set. The image comes from an open access dataset that was collected from 2 actual eye hospitals in Bangladesh. This is important. It's real world data, not a carefully controlled laboratory dataset. The image have real world variations in lighting angle and image quality, which makes the classification task harder and the results more meaningful. And then let's say what models they used. The study used 4 deep learning models. 2 of them are CNN based, Inception B3 and ResNet 50. The other 2 are transformer based, Vision transformer and Swin transformer. Each model is trained independently before being combined. And then assemble method. The combination works by taking the softmax probability output from all 4 models and averaging them together. These averaged probabilities then pass through a final dense layer that makes the ultimate class prediction. And then talk about the data handling. How did they handle the data? To fix the class imbalance problem, smooth is used to generate synthetic addition samples for underrepresented classes. On top of that, standard data augmentations techniques, random zoom, horizon flip, rotation, and cropping are applied to increase the variety of training example. And then the evolution. The models are evaluated using 4 standard metrics: accuracy, precision, recall, and F1 score. These are calculated both for individual classes and for the overall model performance. And then we will talk about the literature review table, where they compares their paper with the 6 other papers. Like in the first paper, the they combined ResNet 15 and ResNet 101 using a DS evidence fusions DS evidence theory fusion technique to classify retinal disease. They achieved 92% accuracy. However, their work only focused on retinal disease. Uh, Internal eye conditions, they did not cover external eye conditions like conjunctivitis or eyelid disorders at all. And then in the second paper, they added bottleneck attention module into a squeeze net architecture to improve feature selection. They achieved 98.9% accuracy, which is quite high, but they only tested on 4 disease categories and did not use any transformer models. And then we have third in we have they used Inception's B3 with transfer learning for eye disease classification and achieved 97.08% accuracy, good result, but again limited to just 3 disease classes and no transformer achieved no transformer architecture was involved. So, and then we go to in these four number research paper where they used MobileNet V2, which is a lightweight CNN variant, and achieved 96% accuracy in low resolution settings, solid work, but fewer disease types were covered in that research paper. And then in 5 number research paper, they applied YOLO V8 and CLS, which is primarily a detection model, and achieved 97.76% accuracy. But this is a detection approach. It identifies what the disease is in a image rather than a multi-class classification approach. So, and then in last paper they used the vision transformer to classify retinal eye disease and achieve 98.1% accuracy, impressive, but they only use the vision transformer. CNN features are never leveraged alongside it. And finally, our study, by combining all 4 architecture into a hybrid ensemble, they achieve 99.12% accuracy across all 5 external eye disease classes. This is the highest accuracy in the table, and it was achieved on the most comprehensive and balanced data set. So now let's talk about the methodology or the pipeline. Now we go to the methodology, the most technical part of the paper. Let me go through each of this part, like data collection, pre-processing. Okay, let's go with the data collection first. The research used an open access dataset for external images. The data set contains 5 disease categories, like previously said: cataract, conjunctivitis, eyelid disorders, uveitis, and I cannot pronounce the normal eyes. And then the images were collected from 2 eye hospitals in Bangladesh. So they represent real world clinic photographers with natural variation in image quality, lightning condition in smoothing angles. This makes the task more challenging but also more realistic. And then we have pre-processing. Before any model can train, the image need to be prepared. All images were resized to like 2 to 4 by 2 to 4 pixel. This is a standard input size for most deep learning models. The pixel value were then normalized using ImageNet statistics, meaning they were scaled to match the distribution the pre-trained models were originally trained on. Additionally, data augmentation was applied: random zoom, horizon flip, rotation, and cropping to artificially increase the variety of training examples and help the model generalize better to new images it has never seen before. And then we have smooth balancing. After previewing, the researcher found that the dataset had class imbalance. Some disease categories have more image than the other. To fix this, they used smooth, which full meaning is synthetic minority overstamping technique, which generates new synthetic training samples for the underrepresented classes by interpolating between existing samples. This ensures the model does not become biased towards the the majority class during training. So, and then we have model training, the most important. But for deep learning models are trained independently on the pre-process and balanced dataset. The 4 models are Inception V3, ResNet 15, Vision Transformer, and Swin Transformer. To CNN models and 2 transform models. Okay, so each models were trained for 10 epochs using the same dataset, the same preprocessing and the same evolution conditions. So the comparison is completely fair. And then we have Ensemble fusion. Once all 4 models were trained, their outputs were combined. Each model produces a softmax probability distribution, a set of numbers that sum to 1, representing the model's confidence for each of the 5 disease classes. This probability distribution for all 4 models were averaged together. The average probability were then passed through a final dense fully connected layer, which makes the definitive class prediction. This approach ensures that the strength of each individual model contribute to the final decision. And then we have evaluation. How to do evaluation? Finally, the performance of both individual models and the ensemble was measured using 4 metrics: accuracy, the overall percentage of correction prediction, and then precision of all the cases the model predicted as a certain disease, how many were actually that disease, and then recall of all the actual cases of a certain disease, how many did the model successfully detect. And then we use F1 score, the harmonic mean of precision and recall, which is the most balanced single metric for evaluating classification performance, especially on especially on imbalance dataset. So and then we will see the model architectures. So let me go deeper into that. Inception V3, which model we use. It is a CNN based. Inception V3 was developed by Google, and it solved a specific problem in CNN, which filter size should be you use. Should you use filter size? Which filter size should you use? Instead of choosing between small filters and large filters, Inception V3 applies multiple filter size in parallel, like 1, 1, 1 into 1, 3 into 3, 5 into 5, in the same layer called an inceptions module. The results are then concatenated together. This allows the model to capture both fine-grained local details and broader structure features at the same. Its accuracy in this study was 93.54%, Inception V3. And then we have ResNet 50. This is also CNN based. ResNet, which stands for Residual Network, was developed by Microsoft Research. Its key innovation is the skip connection, also called a residual connection. In a normal deep neural network, as you add more layers, the gradients used to train the network becomes extremely small. This is called the vanishing gradient problem, and the network stops learning. ResNet solved this by adding shortcut connection that skips over one or more layers, allowing gradient to flow directly backward through the network during training. ResNet 50 specifically has 50 layers. Its accuracy in this study was 83.69%. This the lowest of the 4 models, ResNet 50, suggesting that deeper residual network without attention mechanism may not be optimal for this particular task. And then we will talk about Vision Transformer, or VIT. Vision Transformer was introduced by Google Brain in 2020. Applies the transformer architecture originally designed for neural language processing to image classification. It works by dividing an image into a fixed grid of patches, for example, let's say 16 into 16 pixel patches, and treating each page as a token, similar to a word in a sentence. These page tokens are then processed by a standard transformer using self-attention, which allows each path to directly attend to and communicate with every other page in the image. This means it can capture global context across the entire image in a single layer. Its accuracy in this study was 99.08%, a dramatic improvement over the CNN models. And then we talk about the Swin transformer, developed by Microsoft Research in 2021, improves upon the original Vision transformer by introducing 2 key innovations. First is computes self-attention within local windows rather than across the entire image, which is much more computational efficient. Second, it uses a hierarchical structure like a CNN, where features start a fine separal resolution and gradually becomes coarser at deeper layers. The shifted window mechanism between consecutive layers allow information to flow between neighboring windows, capturing both local and global context efficiently. Its accuracy in this study was 99.10%, the highest of any single models. And then we will talk about the overall accuracy results. The bar chart shows the overall accuracy of all 5 models side by side, starting from the left. Starting from the left, Inception B3 achieved 93.54%, strong result for CNN models, but there is still a meaningful gap from the top performance. And then ResNet 50 achieved 83.69, 83.69%. The lowest of all 5 models, despite being a very well-known architecture, is struggled most with the visual similarity and underrepresented classes. And then Swin transformer achieved 99.10%, excellent performance. And then Vision transformer or VIT achieved 99.08%, almost identical to Swin and clearly in a complete different league from the CNN models. And the hybrid assembly achieved 99.12%, the highest of all. You might look at the difference between 99.10 and 99.12 and think it's trivial, but in medical diagnosis, every fraction of a percentage matters. And more importantly, the important is not uniform. The Ensemble specifically improved performance on the most difficult classes, which I will show you on the next. Here you can see which percentage was which. And now let's talk about the per class F1 comparison. Let's go by class. So first of all, cataract, all models perform well here. Inception B3 gets 0.95, ResNet V2, ResNet 50 gets 0.84, and VIT, Swin and Assembly all achieve over 0.99. Cataract has relatively distinct visual characteristics, so it is the easiest class to classify. And then conservatives, this is where we start to see difference. Inception B3 gets 0.93, ResNet 50 gets 0.84, VIT gets 0.99, Swins gets 0.98, and the assembly gets 0.98. ResNet 50 struggles the most here because conservatives requires recognizing subtle patterns of reduces that CNN architecture can miss. And then we have eyelid disorders. This is the highest class. Inception B3 drops to 0.89, and then ResNet 50 to 0.976. These are the lowest score in the entire table. VIT manages 0.97. Swin achieve a perfect 0.99, and the assembly across achieve 0.99. This is the class where the Ensemble's superiority is most clear. By combining the CNN local texture detection with the transformer global attention, the Ensemble correctly identifies eyelid disorder that individual models would have misclassified. And the normal, all models perform very well here. Inception B3 and ResNet 50 both achieve 0.999, and VIT, Swin and Assembly all achieve the perfect 1. Normal eyes are the easiest to identify, no visible different disease features. And then in last UVTs, Inception V3 gets 0.90, ResNet drops to 0.73, which is concurrently low. And then VIT achieves a perfect 1, Swins gets 0.99, and the assembly achieves a perfect 1. The extremely low score for ResNet on UVTs is a serious clinical concern. UVTs is dangerous, and missing it has several consequences for patients. The overall message from this chart is clear. Transformer models dramatically outperform CNN on the difficult and visually similar classes, and the assembly achieves the best or tied best performance on every single class. And then in last, bring everything together in the conclusion. Now, as stated in the highlight summary, the hybrid assembly combining Inception V3, ResNet 15 Vision transformer and Swin transformer achieved 99.21% accuracy, the highest among all tested models, and outperforming all prior related work on this dataset. And then let's talk about the transformer superiority. Vision transformer and Swin transformer both achieve above 99% accuracy, significantly outperforming the CNN models. This confirms that the self-attention mechanism, which allows the model to look at the entire image simultaneously and understand relationship between distant regions, is more powerful for this type of fine-grained medical image classification tasks. And then assemble advantage: combining four architecture with different strength produce better result than any single model alone. The assemble was most beneficial for the difficult class conjunctivitis and eyelid disorder, where individuals models each made some mistakes, but when combined, they corrected each other's error. Smooth effectiveness: the synthetic overstamping technique successfully balanced the training data. Smooth technique balance the training data. This evidenced by the relatively strong performance even on the majority classes like UVTs, which would likely have had very poor result without the balancing steps. And then clinical potential: 99.12% accuracy AI system for diagnosis external eye disease could be transformative, especially in countries like Bangladesh, where specialist ophthalmologists are not evenly distributed across the country, and AI scanning tool at a rural health clinic could cause serious conditions like uveitis before they cause permanent damage. And let's talk about what Arthur says about the future work. Like in future, right now, when the assembly classification and image and as Europe, as we know, it is correct 99% of the time, but we do not know why it made the specific decision. Techniques like grade cam, shape, and line can generate visual experience, highlighting which regions of the eye image of the model paid most attention to. This is critical for clinical adaptation because doctors need to understand and trust AI decision before acting on them. And then lightweight development: the current assemble of four large deep learning models requires significant computational resource, GPU servers, and large memory. To develop these systems at rural clinic or on mobile devices, the models need to be compressed through techniques like distillation or quantizations, creating lightweight variants that maintain high accuracy but run effectively on low cost hardware. And then larger clinical data sets, as we only took from two hospitals. The current data set came from two hospitals in Bangladesh, which while real world it may not represent the full diversity of eye appearance across difficult thickness, ages, and environmental conditions. Explaining to multi-hospital, multi-country data set would make the model more robust and generalizable worldwide. And then more disease classes. The current model covers 5 conditions, but there are many more serious eye diseases like glaucoma, diabetic retinopathy, age-related macular degeneration, and then corneal ulcers and others. Extending the models to detect these additional conditions would make it far more useful in a clinical settings. And then we have multimodal fusions. And currently, the model only look at the eye image, but in real clinic diagnosis, a doctor could consider the patient's age, medical history, reported symptoms, and other factors. Combining image data with these clinical metadata inputs, called multimodal fusions, could significantly improve accuracy and reduce false positive. And then real-time API integrations. The ultimate goal would be deploy this as a live API that connects to hospital information system, so that where a doctor photographs a patient's eye, the image is automatically sent to the AI, analyzed in real time, and diagnosis suggest is returned within seconds. So these are some future work that can be done on this research paper. And then there are some reference, all the talk they did in their paper. So those papers are where they got that from. And then in last, quickly summarize what we covered today. This paper introduced a hybrid assembled deep learning system that combines two CNN models, Inception B3 ResNet 50, with two transformer models, Vision transformer and Swin transformer, to classify 5 external eye disease from photographs. The key innovation were combining CNN and transformer architecture for the first time in this specific task, using SMOD to handle class imbalance and achieve 99.12% accuracy, the highest reported for this dataset. The result clearly shows that the transformer models dramatically outperform CNNs for this task, and that assembling multiple architecture produce better result than any single models, especially for the most clinically dangerous and visually confusing disease class. This work has real potential to help doctors diagnose eye disease faster and more accurately, potentially preventing thousands of cases of avoidable blindness. I hope this presentation gave you a clear and comprehensive understanding of the paper. I am now open to any questions from my classmates in the comment sections. Thank you very much for watching. Assalamu alaikum.